Let me introduce y'all to my pet, Bufflerd. Bufflerd has been in the family since I was like 3, and he was special because he is super. He can fly. That's why he has these long ears, all right? So let me just show you how he flies. So, just like this, and he raises his ears, and ooh, he flies, right? At least in the mind of a 3-year-old. But I'd like to look a little bit at the physics of what's going on with Bufflerd when he flies. Okay, now we've talked a little bit about kinematics and things, but I want you to pay attention to when I start Bufflerd down here, and as I bring him up and then release him, what you'll notice is that somehow he gains kinetic energy, right? We know that as he goes through the air that he starts to lose kinetic energy, and that turns into potential energy. But what about in that initial phase when I'm throwing him up? Where is that kinetic energy coming from? Now, I know you're thinking, well, you have chemical potential energy from the Fruit Loops that you ate for lunch, and then your body breaks those down, you get the chemical potential. Yeah, but you know what? Sometimes we don't want to worry about all of that, what happened before and what happened, well, where the Fruit Loops get their energy, right? Yes, energy is always conserved. However, it's also important that sometimes you say, you know what? The energy that he got came from the force that I was exerting as I was throwing him up in the air. And when a force is exerted over a distance, we get something that we call work. Now, work is energy, but work is energy that's been added into or taken out of a system. So when Bufflerd and the ground, Bufflerd and the earth were my system, so they gain kinetic and gravitational potential energy, that energy came initially from the force that I exerted on Bufflerd as he went flying up in the air. So that idea of exerting a force over a distance gives work. And work is any energy that has been added into or taken out of a system. The same thing happens when Bufflerd comes back down, right? When Bufflerd comes back down, he's falling with a very high speed. So he's got a lot of kinetic energy. That's because he's fast. So he comes down with a lot of kinetic energy, and I catch him. And when I catch him, all of a sudden, all of that kinetic energy is gone. Well, where did it go? I exerted a force on him over a specific distance. And when I exert that force over a distance, I do work. I either add energy into the system, or in this case, I take energy out. Let's look at another situation. You guys know about foosball. The ball just sits there until the guy kicks it. Now, the process of the guy kicking it is a force over a short distance, and that is when the guy kicking it does work. He adds energy to that ball that did not have energy before. Now, in this one, you'll notice that the guy kicks it, doing work on the ball, causing it to gain energy, and then it'll run into the other guy. The other guy is going to exert a force in the opposite direction, causing it to slow down, therefore taking energy out. Both of these are considered work. All right, so let's step back to that original example of Super Bufflerd flying up in the air, because he's my favorite. So let's look really quick. When I am holding him in my hand, what are the forces acting on him? Well, you got the force of gravity, and you've got the normal force of my hand, right? And those are the only two forces acting on it. And those two should be the same, all right? So I'm going to mark them the same because I'm not very good at drawing. So there we go. We got those two forces being the same. Now, when I'm throwing it, something has to change. He needs to be able to accelerate upwards. Now, that means that the force of gravity, of course, is going to stay the same. But now, the normal force of my hand needs to be even larger. If the normal force of my hand is not larger than the force of gravity, then he wouldn't accelerate upwards. And so therefore, my hand, that's Newton's second law, right? In the first situation, we know that he's at rest and staying at rest, therefore the forces must be balanced. There must be no net force. In the second situation, he is accelerating, therefore the forces must not be balanced. There must be a larger force upwards in the direction that he's accelerating. All right? Now, once he's in the air, the only force present is the force of gravity, which is the same as it was the whole time. And it doesn't matter whether Bufflerd is going up or down, the force of gravity is always downwards. All right? Now, in this situation, one of the things that we want to note is that my hand is doing work, right? My hand is adding energy into the system. Now, the way that works, remember initially, Bufflord wasn't moving. In order to have work done, work is defined as the change in energy of a system. Okay, so in order to have work done, then we need to have a change in distance. Remember, we talked about the idea that it's force exerted over a distance. So when you multiply those together, you get the amount of work done. So here at the beginning, no work is being done because even though there's forces, it's not being exerted over a distance. And so therefore, the object doesn't gain or lose any energy. It just stays where it is. Now, in this second part, when I'm throwing it, my hand causes it to move upwards. And so as the force of my hand has a larger force than the force of gravity, it's going to then do some work. My hand is going to exert some force. That force will be across a certain distance, and my dog Bufflord is going to gain both kinetic energy and gravitational potential energy, as long as we're talking about him and the Earth system. All right, now what would this look like in our equation? Well, work is the change in energy. Now in this case, when he starts here, down at my waist, and then as I push him up and I release him a little bit above that, maybe at my shoulder height, then there's that distance that's being covered. Two things are happening. Number one, he's getting faster, which means that there's a change in kinetic energy. And number two, he's getting higher, which means that there's also a change in gravitational potential energy. Both of those things are happening as I throw Bufflord upwards, as he gets into his speed to fly up in the air. So during that time, we do want to make sure that we talk about both of those pieces. So we've got, remember that delta is the change, so that's the final kinetic energy minus the initial kinetic energy. And then we'll go plus, and then the same thing for the gravitational potential energy here, so that's UG final minus UG initial. The change is always the final minus the initial. So now we look at those and we say, well, when I was holding in my hand, if I make that my height 0, this is one of the neat things about gravitational potential energy is that we can define height 0 wherever we want it to be. I can make it the lowest that my dog ever is. And so that's going to be gravitational potential energy 0. So at this lowest point, it didn't have any speed, which means he didn't have any kinetic energy. And it didn't have any gravitational potential energy, which means because it didn't have any height there either. So what we're left with is simply that the amount of work done is equal to whatever kinetic energy he has as he leaves my hand, plus the gravitational potential energy that was gained over that height of d. So essentially what this is saying is that the energy that I end up with is equal to the amount of work that was done on Bufflord as I was throwing him up in the air. Now, that work is going to depend on how much force I exerted on him and the distance over which I was exerting that force. We can get information about that if we like. I mean, for example, we do know that kinetic energy is 1/2 mv squared. Now, I could get the mass by just measuring Bufflord, but then I could actually use this idea of the final velocity. That's the velocity with which I threw him. We could get that from kinematics or from something else. We could figure out just by measuring maybe how high he went, right? I could figure out how fast he was going. Of course, I can measure the mgh. Again, I can measure the mass. I know g is 9.8, and the height is just how high he was when I threw him. Now, once he's in the air, remember, the only force is gravity. So once I release him, I'm not doing work on him anymore. The only force is gravity. And gravity is accounted for if we're talking about the Bufflord Earth system. Gravity is it is a force, but it would be internal to that system. It would not be an outside force that is doing work on Buffalo. All right. So if we wanted to look at what would happen in the air after that, then we could say, well, energy will be conserved from when I let go of him until right before I catch him again, right? So as Bufflerd flies up in the air, the only force on him is gravity. And so if that's the only force, then energy should be conserved from when I let go until I catch him again. All right? So we could then go to this same idea of work equals change in kinetic plus change in gravitational potential energy. But in this situation, once we write it out and say that means the final kinetic minus the initial kinetic plus the final gravitational minus the initial gravitational, we could say, well, when he's in the air, there are no other forces other than gravity, which is accounted for in our gravitational potential energy. So therefore, there won't be any work done because there aren't any forces acting over that distance. So work would be 0. Then, depending on whether we want to look at the point where I catch him or the point up in the air, that would then affect whether there is final kinetic or gravitational potential energy, or if there is initial kinetic or gravitational potential energy. And so we can use this principle to help us to solve for things, much like we did with kinematics. So let's say that I used my kinematics and I was able to figure out that the speed when I threw him was about 5 meters per second. All right? I used my mass balance and found that he was 0.5 kilograms. Can I find out how high he goes up in the air based off of, let's just say, from where I release him? So how much higher does he go from my hand after I release him? So let's go ahead and look at the equation that we just made. So we've got the final kinetic energy, which would be at the maximum height, that would be up here. So what is our kinetic energy up at this point? Hopefully you're recognizing that the final kinetic energy will need to be 0 because at that maximum point, the velocity is 0. Just like when we did kinematics, right? When you get to the maximum point, for that instant, velocity is 0. So that means my final kinetic energy, if I'm looking from when I release it until it gets up to that maximum height, the final kinetic energy will be 0. The initial kinetic energy is going to be 1/2 times m, which is 0.5, times the velocity squared. And we said that I measured using kinematics or maybe a motion sensor or something that when I released him, he was going 5 meters per second. All right. Then we're going to go plus the final gravitational potential energy. So remember, gravitational potential energy is mgh. So that's going to be the mass of 0.5 times the g of 9.8 times the height, which is what we're looking for. That's going to be that maximum height above the release point. Then if we do the math there, then we end up getting that the maximum height above the release is about 1.28 meters. All right, and that's just by doing the math, moving it over, and solving for h. So over the next couple of days, we'll do a few more examples of this just so that we can get used to how we use conservation of energy. All right, just like this, you'll practice with a couple of things. We'll do a lab and work some problems in class, and hopefully you'll get used to the idea of situations where we have work being done, outside forces acting on our system, and then we also have situations where no work will be done and energy will just be conserved. So I hope that was helpful, and like I say, we'll continue to work on that in class. See you next time.